Dementia risk study using 3 VPT methodologies. Solid-VMT, Fluid-VMT, and TDA research methodologies. Number 1474, VPT Sharp 035, December 21, 2025. Gerald C. EclaireMD Foundation. Category: Dementia, Vascular Medicine, Metabolic Disease. VPT Methodology. Preface: I write this study not to diagnose dementia, since I have no clinical signs of dementia, but to quantify my dementia risk as a long-term, system-level process. Therefore, this article belongs to preventive medicine research. Dementia does not suddenly appear. It is silently prepared over decades through vascular stiffening, metabolic toxicity, impaired cerebral circulation, and cumulative physiological stress. By the time clinical symptoms are diagnosed, most of the underlying damage has already occurred. Traditional dementia research often focuses on late-stage outcomes such as cognitive scores, imaging findings, or pathology. These approaches describe what dementia looks like, but not how dementia risk is progressively built. Therefore, this article focuses on dementia progression and trajectory rather than end-stage treatment. Because no dementia has been diagnosed, this study intentionally emphasizes Viscoplastic Medicine Theory, Fluid-VMT, to investigate dementia risk progression and trajectory. Solid-VMT is included only as a secondary supportive tool to summarize cumulative stress-strain energy contributions. The quantitative calculations are identical for both fluid-based VMT and solid-based VMT. Therefore, my proprietary VMT AI software, Chronic, is utilized for the numerical computation component of this study. This study introduces a novel quantitative framework, Viscoplastopology, VPT, to model the long-term trajectory of dementia risk by treating neurovascular and metabolic stress as physical energy inputs. We utilize Viscoplastic Medicine Theory, VMT, to identify the pivot point where risk accumulation stabilizes. Complementary Topological Data Analysis, TDA, confirms that early metabolic correction leads to a more stable physiological state space, providing a mathematical foundation for preventive interventions decades before clinical onset. Introduction. Dementia is not a single disease entity. It is the final manifestation of multiple interacting failures, particularly chronic vascular injury and long-term metabolic stress. Vascular dementia and mixed dementia represent a substantial portion of real-world dementia cases. From a physical systems perspective, dementia risk behaves like a viscoplastic process because stress accumulates slowly over time. Deformation is largely irreversible. Early damage dominates late outcomes. Recovery is asymmetrical and limited. These characteristics make dementia risk especially suitable for analysis. Using Viscoplastic Medicine Theory, VMT, with the addition of mathematics-based geometric topology methods, I have expanded VMT into the broader framework of Viscoplastopology, VPT. In this study, the dementia risk proxy, DRP, is treated as an output strain variable evolving under the influence of 4 input stressors. 2 physics-based VMT perspectives are applied with clearly differentiated roles. Fluid-VMT serves as the primary analytical framework, focusing on dementia risk progression, timing, and trajectory. Solid-VMT serves as a secondary analytical framework, summarizing individual stressor energy contribution ratios and cumulative energy contributions over time, without implying disease end stage. Topological Data Analysis, TDA, is used as an additional lens to validate and complement these 2 physics-based approaches. Brief method descriptions. Study design and data. This is a single subject, myself, longitudinal, preventive medicine study, using 16 annual data points collected from 2010 to 2025. The dataset includes metabolic, vascular, and physiological indicators, measured consistently over time. Strain variable definition. Because dementia has not been diagnosed, a proxy strain variable is required. The dementia risk proxy, DRP, is defined as a normalized composite index, representing long-term neurovascular and metabolic burden. DRP is calculated annually as stressor variable definitions. 4 stressors are included. Vascular calcification proxy equals the sum of PP divided by 45, MAP, divided by 85, and E/G divided by 120, all divided by 3. FPG, fasting plasma glucose, representing chronic glucose toxicity. Health age, a composite biological aging indicator, derived from 4 metabolic biomarkers and 6 lifestyle factors. Body weight, a simplified obesity proxy. Normalization constants represent clinically meaningful reference values. VPT analysis. 2 VMT and TDA. Fluid-VMT is used to analyze and interpret the temporal evolution of DRP, focusing on progression, inflection points, and cumulative energy accumulation over time. Solid-VMT is used to compute the contribution ratios of the 4 selected stressors, and the cumulative energy contribution changes from each stressor across the entire study period. Topological Data Analysis, TDA, provides a mathematical lens to examine data point connectivity, geometric shape changes, and system stability. Definition and interpretation of the 4 stressors. Vascular calcification proxy, VCP. VCP reflects cumulative arterial stiffening and calcification tendency, which impairs cerebral perfusion stability. The stable, adequate, and well-regulated supply of oxygen and nutrients to brain cells, and damages microvasculature through cerebral vascular calcification and stiffness. Vascular rigidity is a dominant pathway in dementia risk preparation. In VMT terms, VCP represents irreversible structural deformation energy. FPG, fasting plasma glucose, is measured in the early morning after overnight sleep. It reflects long-term glucose toxicity and insulin resistance burden. Chronic hyperglycemia accelerates endothelial injury, promotes vascular calcification, and disrupts brain energy metabolism. Glucose toxicity often precedes vascular damage by many years. In VMT terms, FPG represents sustained biochemical stress input. Health age reflects biological aging rather than chronological time. It summarizes cumulative physiological stress from multiple metabolic and cardiovascular factors and is therefore more appropriate than real age for healthcare research. Body weight serves as an indirect metabolic stress amplifier, although weaker and more indirect than hyperglycemia or vascular stiffness. Excess body weight contributes through inflammation, insulin resistance, and increased vascular load, which promote the development of type 2 diabetes. Diabetes is one of the primary inputs contributing to stroke, dementia, and cancer. VPT analysis results. DRP strain trajectory. In Fluid-VMT interpretations, the calculated DRP values show a clear long-term decline from 2010. DRP 143, through 2025, DRP 86. DRP decreases from approximately 143 in 2010 to approximately 86 in 2025, representing about a 40% reduction in dementia risk strain. The trajectory exhibits high dementia risk strain during 2010, 143, to 2012, 136. Rapid improvement during 2013, 113, to 2016, 101. Minor oscillations during 2017, 101, and 2019, 102. Progressive stabilization and flattening after 2020, 95, through 2024. 91, to 2025, 86. These small rebounds are physiologically realistic and reflect normal metabolic and vascular variability within a recovering system. Fluid-VMT interpretation. Fluid-VMT analysis shows that most dementia-related stress energy accumulated early in the study period, after metabolic and vascular correction. Incremental risk accumulation became minimal. The cumulative VMT energy levels reached 88% in 2014 and 92% in 2017, indicating that the period from 2014 to 2017 represents the pivot point of significant dementia risk of DRP reduction. This indicates that dementia risk is a long memory process, dominated by early and midlife conditions. Later lifestyle interventions primarily slow progression, rather than reverse accumulated damage. Solid-VMT interpretation. Cumulative VMT energy contribution percentages. Solid-VMT analysis quantifies cumulative energy contribution ratios across the full 16-year study period. The Solid-VMT results show VCP contributes the largest share of total energy, 28%. FPG contributes nearly as much as VCP, 27%. Health age contributes a substantial but secondary share, 25%. Body weight contributes the smallest share, 20%. These findings confirm that dementia risk is driven primarily by vascular rigidity and glucose toxicity, with obesity and aging acting as supporting contributors. In this study, Solid-VMT does not represent disease end stage. It serves only to summarize relative contributions within a preventive framework. Topological Data Analysis, TDA, of dementia risk trajectory. TDA methodological rationale. While Fluid-VMT quantifies how dementia risk evolves over time, and Solid-VMT quantifies cumulative stressor contributions, neither method explicitly describes the geometric structure of the underlying data. Dementia risk, however, is not only an energetic process, but also a geometric one, characterized by changes in geometric shape, data point connectivity, and stability of multidimensional pathophysiological states. Topological Data Analysis, TDA, is therefore introduced as a complementary analytical lens. TDA focuses on the geometry of data point distributions, including their connectivity, clustering, contraction, and long-term structural evolution, rather than on statistical averages. regressions, or linear correlations commonly used in traditional medical research. In this study, TDA is used to examine how the dementia risk system transitions from an unstable, high-risk, geometric configuration to a more compact and stable configuration over time. Data representation for TDA, each year from 2010 through 2025, is represented as a point in a four-dimensional stressor space defined by N1, VCP, vascular calcification proxy, N2, BW, body weight, N3, FPG, fasting plasma glucose, N4, health age. Thus, each annual state is a point in a four-dimensional geometric space, describing vascular, metabolic, and aging-related stress. The DRP value is treated as an output strain indicator, and is not used as a coordinate in the TDA space. Instead, TDA focuses on the geometry, formed by the four stressors that drive DRP, geometric evolution of the data cloud. Early period, 2010 to 2012. During the early period, the data points are widely dispersed in the four-dimensional space. VCP, BW, and FPG all exhibit high values, and health age is elevated. The geometric configuration is expanded, indicating a high-energy, unstable system with weak internal coherence. From a TDA perspective, this corresponds to a loose, scattered point cloud with low connectivity and high geometric volume. Such a configuration is characteristic of high dementia risk preparation. Transition period, 2013 to 2017. Between 2013 and 2017, a clear geometric transition occurs. The data points move inward toward a more compact region of the stressor space. FPG shows a strong downward shift. BW decreases steadily, and VCP stabilizes and gradually declines. Health age also improves significantly during this interval. Topologically, this period represents contraction of the point cloud. Connectivity among data points increases, and the overall geometric shape becomes smoother and more coherent. This transition corresponds exactly to the Fluid-VMT pivot period, identified earlier, during which cumulative dementia risk, energy accumulation slows dramatically. Stabilization period, 2018 to 2025. After 2017, the data points form a relatively tight cluster, with small year-to-year movements. Although minor oscillations occur, the overall geometric structure remains compact and stable. No large expansions or fragmentation of the point cloud are observed. From a TDA standpoint, this indicates that the dementia risk system has entered a stable basin. The system remains sensitive to perturbations, but no longer exhibits large-scale geometric instability. Data connectivity and geometric stability interpretation. TDA emphasizes connectivity rather than magnitude. In this study, increasing connectivity among yearly data points reflects improved internal coordination among vascular, metabolic, and aging-related variables. Reduced geometric dispersion corresponds to lower systemic stress and improved resilience. The absence of topological breaks or bifurcations after 2017 suggests that dementia risk progression has been effectively damped. Even though chronological aging continues, integration with fluid and solid VMT, the TDA findings strongly reinforce the conclusions drawn from both fluid and solid VMT. Fluid-VMT identifies early accumulation and later flattening of dementia risk. Solid-VMT identifies vascular stiffness, VCP, and glucose toxicity, FPG, as dominant contributors. TDA shows how these energetic changes manifest geometrically as contraction, stabilization, and improved connectivity of the physiological state space. Together, these three research models describe dementia risk from complementary perspectives. Fluid-VMT explains when and how risk accumulates. Solid-VMT explains which stressors dominate. TDA explains how the system reorganizes geometrically toward stability. Preventive medicine interpretation. Because no dementia has been diagnosed, the TDA results are interpreted as evidence of successful risk trajectory modification rather than disease reversal. The geometric contraction observed after 2014 indicates that early and sustained metabolic and vascular correction can move the system away from high-risk topological configurations, even in the presence of aging. This reinforces the central preventive insight of this study. Dementia risk is modifiable, primarily through early intervention that reshapes the system trajectory, long before clinical symptoms appear. Below is a proposed translation and integration framework for my paper. 1. The biological battery, Fluid-VMT. 2. The biochemical versus structural drivers, Solid-VMT. 3. The systemic resilience map, TDA. Disclaimer: this content is provided for educational reference only, and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and related materials belong to the author, Gerald C.